So next we're going to talk about lines and planes. Now lines, of course, we have an understanding from just two-dimensional algebra. So today we're going to proceed with this idea of how do we generalize this to 3 dimensions, and we'll see it actually generalizes to any number of dimensions. And of course, as we've already seen in a very simple way, once you're in 3-dimensional space, you can have these things that are planes. And then we're also going to talk about how to use the formula for planes, and also we're going to see some applications of these things. Okay, so first of all, lines. In 2 dimensions, a line is determined by a point and a slope. Now, it's going to be useful for us to recognize that saying what the slope is conceptually equivalent to giving a direction. Okay, so we're going to rewrite this using parametric equations. And once again, our parameter is going to be t. So x and y are essentially going to be functions of t. So how do we do that? So imagine we got a point and a slope. So imagine we have the point AB and the slope is m. So this is stuff that we've seen before. So how would this look parametrically? The initial value for x is a, and for our purposes, let's just say that x changes the same as t. So x as a function is just the value a plus our parameter t. So notice that means if t changes 1, x changes 1, we want a simple relationship like that. Okay. For now. So for y, the initial value is b. And as x changes, which is the same as t changes, we know that as x changes 1, y changes m. So y equals b plus mt. So that becomes this system of parametric equations: x equals a plus t, y equals b plus mt, and that's just the standard. That's just how you write it parametrically for a standard kind of line in 2 dimensions. Okay, and just a quick comment: if you take those, what if you go backwards? If you take those 2 parametric equations, if you eliminate t, notice that t equals x minus a, so then y equals b plus m times x minus a. And that is really just the point-slope form of the equation of a line that you've seen before. Okay, so now we've just engineered it into parametric form. Okay, well now we're going to take the next step, which is to turn that into vector notation. So in vector notation, we just pair it up, we just put vector brackets around it basically. So we get this: xy equals a plus t, comma, b plus mt. Okay, that's just notation. But now we're going to do something very clever using our concepts of vectors. So to find the general vector formula and to put it nicely, we're going to split this into a constant part and a variable part. So we're going to break up the vector on the right side, and now it looks like this. And you can do the calculation in your head and go backwards to see it's the same thing. So now, another notation change. We're going to call our xy variable vector, we're just going to call it r. R is the position vector. And then we're going to say AB is our known value. So instead of saying x0, y0, we're going to call that r0. That's a vector. And then 1 comma m, which represented our slope, we're going to say that represents a direction. So we're going to say that's the direction vector v. So in that notation, we get this. R equals r0 plus v times t. So one quick comment. V is the direction vector. So you can multiply v by any constant. It'll still represent the same direction. So it'll still represent the same line. So notice that as t changes, r changes. And that gives you sort of like your variable point on the line, which could be anywhere on the line. All right. And notice that this formula the way it's written in vector notation, doesn't say anything about 2 dimensions or 3 dimensions or how many variables you have. Or excuse me, how many, I should say how many components you have. This could have x and y components. Your vectors could have x, y, z components. They could have x, y, z, w. You could have as many components as you like. So this really works for any number of dimensions. And let's see graphically how that works. So here I've just got the graph of some line and I've put it in 3 dimensions. And of course, remember, because perspective is tricky in 3 dimensions, you just have to sort of imagine that line is floating in 3-dimensional space. So what does this mean? So you've got an initial point, which is anywhere on the line. So I'm just going to stick it here. So that is our 0. Now, what's v? V is the slope, or it's more helpful for us to think of it as a direction. Yeah, in a sense, it's the slope, but it's more precise to say direction for reasons we'll see later. So v is just the direction. So
it's the direction because 3-dimensional.
There you go. Yeah. Direction is sort of like the multi-dimensional generalization of slope. Slope does have a meaning. We're going to get to that later. Okay. So that is v. Now, of course, we said v just represents the direction. So there are lots of different vectors that represent the direction of the line. Any of those could be your v. So v could be this, v could be this, v, as we know, could go in the other direction, et cetera, et cetera. And what does t do? T is basically your multiple of v. So t tells you how far to go in that direction. So if t says go a certain amount far, then you've gone over here, and that means you're not talking about that point on the line. So if t is negative, going the opposite direction, that means you go here, and that means now you're at this point on the line. So all the different values of t represent all the different points on the line. So now let's use all this to do some problems. Okay. So find the equation of a line through the point 0, 4, parallel to 1, 2. So write the answer as a vector equation, as a system of parametric equations, and then I'm going to connect that back to our standard representations. Okay. So how do we do this as a vector equation? Well, it's just r equals r0 plus vt. So we've got all these things. So we just have r. You can write r or xy, same idea. So r equals r0 is the known point, which is 0, 4, plus our direction vector, which is 1, 2, times t. That's it. And again, if you like, you can write r as x, y. So that's the answer to A. The answer to B is system of parametric equations. So you get x equals 0 plus 1t, and y equals 4 plus 2t. Okay. Oops. All right. So now, what about C? So what is the slope? Well, the slope comes from the direction that we're traveling in. So the direction that we're traveling in is dictated by the direction vector, which is 1, 2. So the vector 1, 2, what does it tell us about changes in y versus changes in x?
Changes in x is a different slope than change in y?
Yeah, exactly. Every time x goes 1, y goes 2. So your slope is 2. Now don't be distracted by the fact that I wrote dy dx, right? Even though it looks like calculus, because this is a straight line, we know that slopes are constant, and you can just say change in y over change in x. Okay.
I think the delta y is negative, right?
So finally, what's the standard equation y equals f of x? Well, this one actually works out really nicely because you just get x equals t. So the standard equation would just be y equals 4 plus 2x. Or y equals 2x plus 4 if you prefer that. Okay. So some comments, right? So we have this thing where we write down p comma q. Now we talked before about there's this ambiguity in that it could on one hand refer to a point and the other hand refer to a vector. So it's both simultaneously. The question is, how do we use it? Well, think about what the question tells you. It says the line goes through 0, 4. So that's a position. So treat that as a point. And then it says parallel to 1, 2. That's a direction. So you have to think of that as a vector. Now, computationally, there's no difference. But in terms of how you use them and how you think about them, if you want to understand, for example, where to plug them into formulas and stuff, you should understand that sometimes one of them plays the role of a point for a position, and in other cases it plays the role of a vector for direction. Okay? So now we'll do this problem in 3 dimensions. Find the equation of the line through this point, negative 2, 4, 5, and parallel to this, 3, 4, 2. So once again, keep in mind, through a value, we have to think of it as a position, so it's a point. Parallel to, that means we want to think of that as a direction, so treat it as a vector. Okay? So, once again, you just get r equals r0 plus vt. So it's r equals the known point, negative 2, 4, 5, plus v, the known direction, 3, 4, 2, times t. And that's a, and then as a system of parametric equations, you just get x equals negative 2 plus 3t, y equals 4 plus 4t, z equals 5 plus 2t. And I stacked them to make it even more obvious about how you go back and forth between the two representations. Here's a question to think about that we will ask now and then answer later in the course. And it's connected to one of the key and most important ideas in this course. What is the slope of this line? What does that mean? Okay. Okay. So this is, as you can see, this is a very straightforward way to write down the equation of the line. So right now we're going to learn one other way. So it's called symmetric equations. And this allows you to write it down only in terms of your variables x, y, and z, and without the parameter t. So the way that you do it is you solve for t. So think of the system of parametric equations. In each one, solve for t, and then set each of those things equal to each other. So let's do that. So we just solved. So notice that we just solved the line through negative 2, 4, 5, parallel to 3, 4, 2. We just solved that. So now let's write this down in symmetric equation form. So for x, when we solve for t, you get x plus 2 over 3 equals t. And then from the y equation, you get y minus 4 over 4 equals t. And then from the z equation, you get z minus 5 over 2 equals t. So now, to get the symmetric equations, you just write x plus 2 over 3 equals y minus 4 over 4 equals z minus 5 over 2. And so one way to interpret this graphically is to say, or even algebraically, is to say x, y, and z, they can all be any value, but once you know one of them, that tells you what point you're at on the line. So from that, you should be able to find both y and z. And that's what the symmetric equation allows you to do directly.
If you know one of them, you know all of them.
If you know one of them, you know all of them. Exactly. Okay. So the symmetric equation is set up to do specifically that. Okay. So here's another kind of problem that we now know how to do. Find the equation of a line given 2 points. But now we're going to do this in 3 dimensions. So how does that work in 3 dimensions? So find the equation of the line through these 2 points, 2, negative 3, 1, and 5, 2, 0. So how do we do that?
But now we know it's going through 2 points, so there's 2 positions.
Right.
We need to find the vector.
Exactly. We have 2 positions, we have 2 points. In 2 dimensions, you say find the slope. But now we're in general dimensions, in this case 3 dimensions, and we know how to use vectors. So what we find is the direction vector. Exactly. So you find v just by taking one minus the other. And again, it doesn't matter which one you use. So I'll say it's going to be 2, negative 3, 1, minus 5, 2, 0. And that gives me negative 3, negative 5, 1. There's my direction vector, and now I can just go down. I go directly to writing down the equation. So I know that r equals r0, a known point. Now, does it matter which point I use? Doesn't matter which point I use. I just have to start on the line and then go in some direction. So just for fun, I'll use the first one, 2, negative 3, 1. Plus my vector, my direction vector, which is negative 3, negative 5, 1, times t. And there's the equation of the line. Next, planes. Okay. So to determine a line, we need a point and a vector, which is the same as saying a direction. Or 2 points, which we can use to give us a vector. Okay. In 3-dimensional space, what determines a plane? So, a plane can be determined by either 3 points, or a point and 2 vectors in the plane. And I think those two sort of geometrically make sense. For 3 points, think of just drawing the triangle, and there's your plane right there. A point and 2 vectors. 2 vectors determine a plane, and then the other point tells you sort of like the position of the plane in space. And here's another one. A point and 1 vector which is perpendicular to the plane.
Okay, so if we have a, yeah.
And another word for perpendicular is normal. Now it turns out, even though 3 points and a point and 2 vectors are the easiest to visualize geometrically, it turns out that to write down the equation, a point and a perpendicular vector, or what we're going to call the normal vector, that's the easiest way to do it. So let's go through how to do that. Okay. So assume that the point in the plane that we know is P, x0, y0, z0, and the perpendicular or normal vector is n for normal, and that's ABC. So now we're going to derive the equation where this comes from. So for any point in the plane Q, x, y, z, so this is like our R vector from before. The vector PQ is perpendicular to n. Right? This is what we were saying. Any point in the plane is perpendicular to this normal vector. So when they're perpendicular, the dot product is 0. Now let's write that down and see how it gives us the equation. So the vector PQ dot n equals 0. Well, now let's write this down. So the vector PQ is the difference between the 2 points. So it's x minus x0, y minus y0, z minus z0, dot ABC. So what is that? Let's just write out the calculation. So you write out the calculation, then I'm going to combine the constants, and what you get is this. So this is considered the standard form for the equation of a plane. AX plus BY plus CZ plus D, our mystery constant, equals 0. And notice that if the equation is written like that, what do you immediately see? You immediately see the normal vector for the plane. The normal vector is just ABC. Okay. Now, doing this derivation gives us another way to write down the equation of a plane, depending upon what information we're given. Suppose we're given, let's see, the point and the normal vector. You could just write it down like this. And then write down the components. But to write it down as vectors, you can write it down like this. Okay. So here is a plane in 3 dimensions. And what I've drawn in purple is the normal vector. So you can get a visual idea, if you didn't have it before, that all you need to describe is some point, any point in the plane, and the normal direction. Now notice that it can be any point in the plane. You could specify this point and this normal vector. Or you can specify this point. And then the normal vector is again going to be this. It's going to be parallel. So notice that no matter which point you start at, every vector coming out from that point, and by every vector, I'm saying every point in the plane, because every point in the plane determines a vector, is going to be perpendicular to your normal vector. So visually, that's what that means. So now if I simply give you these objects, then it's easy to write down the equation. So what's a little more work is we said that 3 points determines a plane, but if you have 3 points, you can't just take those numbers and write down the equation directly. So how do you do it? Well, 3 points, we can use those points to determine vectors in the plane. Just like before we had 2 points determine a line or a vector, now we've got 2 points that gives us one vector. And take a different 2 points, that'll give us another vector. And what can we do with those 2 vectors? Take the cross product. And that gives us the normal vector. So for example, let's use these 3 points, and let's make the equation of a plane. All right. So we need 2 vectors. So I'm going to have V and U. So I'm going to use P and Q to make my first vector. So let's see. So I guess I'm technically doing QP. I'm going to do 2, 5, 1 minus 0, 3, negative 2. And that gives me 2, 2, 3. So that is one vector that actually lies in the plane. Okay, next. Next one, just because I feel like it, I'm going to use QR. And that is 6, 1, 2 minus 0, 3, negative 2. And that works out to be 6, negative 2, 4. So now we need the normal vector. So the normal vector comes from the cross product. So that's 2, 2, 3 cross 6, negative 2, 4. So now we have to do this. How do we do this? So for the first component, you take the cross of the second and third components. So it's 2 times 4, which is 8, minus 3 times negative 2, which is negative 6. 8 minus negative 6 is 14. Next. We want the second component, so we can take the cross of the third and the first. So it's 3 times 6, which is 18, minus 4 times 2, which is 8. So 18 minus 8, 10. Next. Third component, take the cross of the first and the second. So it's, for example, 2 times negative 2 minus 6 times 2. So that's negative 4 minus 12. That's negative 16. So there's my normal vector. So we're almost done because now we know the equation of the plane is 14x plus 10y. Oops. Minus 16z plus d, our mystery constant, equals 0. So how can we find the mystery constant?
Use a point.
The easiest way is just to use one of the known points because it has to work.
It looks similar to the equation of a line extended form. What is it? AX plus B.
It's very similar to the equation of a line in standard form, and that's not a coincidence. It's because this pattern, this form, works in any number of dimensions. Okay. So let's see, I'll use one with 0 in it because that'll be easiest. So 14 times 0 plus, keep it consistent, plus 10 times 3 minus 16, negative 2, plus d equals 0. So that's 30 plus 32 plus d equals 0. So you get d equals negative 62. So finally the equation is 14x plus 10y minus 16z minus 62 equals 0. Can use any point. Sure.
To determine the constant is what you're asking?
Right. So to determine the constant d, you can use you can plug in any point. Right. Just like when you're think back to beginning of algebra, when you have y equals mx plus b, you find the slope and then you want to solve for b, your constant. Which point can you plug in? Any point. Any point has to work. Also, I used these two I used PQ and QR to find my two vectors. Does it matter which vector? Does it matter which pairs of points I use? No, it doesn't matter. At the end of the day, you're going to wind up with the same or an equivalent equation. Speaking of which, we can actually simplify the final equation. Now, you don't have to, but what can you do to simplify this last equation? you can divide by 2. So equivalently, you get 7x plus 5y minus 8z minus 31 equals 0. You don't have to do that, but you can. Now I want to talk about applications regarding lines and planes. Applications in the math realm. Okay. So, what about the direction of a plane? Well, the easiest way to describe the direction of the plane is by simply referring to the normal vector, because we know how to talk about the direction of a vector. Therefore, two planes are parallel if the normal vectors are parallel. And the way you do that is if your normal vectors are n1 and n2, two vectors are parallel if one is a multiple of the other. They're in the same direction. Okay. Two planes are perpendicular if their normal vectors are perpendicular. Or in other words, the dot product is 0. Okay. More generally speaking, so that's parallel and perpendicular. Those are only two possible orientations. We know how to do, so that's just an angle of 0 and an angle of pi over 2. We know how to describe any angle. The angle between two planes is the angle between the normal vectors. And we know how to find the angle between two vectors. So, find the angle between these two planes. 4x plus 3y minus z minus 5 equals 0. And negative 2x plus 5y plus z plus 2 equals 0. Now, this in the abstract, this seems like a very complicated problem. But it's actually simple. Because in order to do this problem, you need the normal vectors. Well, what's the normal vector for the first plane? 4, 3, negative 1. You just pull off the coefficients.
What about the 5, the negative 5? It doesn't matter?
And the constant negative 5, does that tell you about the direction of the plane?
No, it wouldn't.
It tells you about the position of the plane, which has nothing to do with its direction.
It wouldn't change the angle.
And doesn't change the angle, exactly. So there's your first normal vector. And so your second normal vector is negative 2, 5, 1. And to get the angle, we take the dot product and then divide it by the magnitudes.
And take the arc.
So that's, yeah, right. That's the cosine. So cosine theta is the dot divided by the magnitudes. So the dot product is minus 8 plus 15 minus 1 over the magnitude of the first one. It's going to be 4 squared plus 3 squared plus 1 squared. And then we're going to multiply that by 2 squared plus 5 squared plus 1 squared. And again, I'm dropping the sign because it gets squared anyway, so it doesn't matter. And so this gives 6 divided by, whip out your calculator. So this works out to square root 26, square root 30. That's 6 over rad 780. Okay.
That would be 1.3354 doing
Okay. So there you go. So that's the direction and the angle, direction of a plane and the angle between two planes. Next, when you have two planes, either they can be parallel and they'll never meet, or they can cross. If they do cross, notice that they'll intersect in the shape of a line. So naturally, we want to find out what's the line, what's the equation of that line. So how do we do that? Well, there's two different ways. one way is to like set up a bunch of equations and just to solve it out using in a typical algebraic fashion. So let's find the line of intersection between these two planes. So the way to do this is we're going to write the equation of the line in parametric or vector form, and so we're going to just call one of our variables the parameter. So let's say x is our parameter. So we're going to call that. So we're going to say just x equals t. And now we're going to solve for y and z. So we get y as a function of t and z as a function of t. So if x equals t, let's plug in. And you get 4t plus 3y minus z minus 5 equals 0. And then the other equation, you plug in x equals t, you get this. And now you can simplify and reduce. And you get 2t plus 8y minus 3 equals 0. We eliminate z. And now you can solve for y. So you get y equals 3 minus 2t over 8. Now once you have that, you can plug that back in order to get an equation for z. So one by one, we're getting an equation for x, equation for y, equation for z in terms of t. So you do that algebra, and you get z equals negative 31 plus 26t over 8. So now that you have each of those, that's your equation of the line, and you can write it in any form that you want. You can write it in system of parametric equations form, which we basically already just have. Or I like writing it in vector form. So vector form, you write x, y, z equals the constant part plus the variable part, which is the direction vector times t. But again, any form of the solution is correct.
Is that like saying y and z?
So that's the regular algebra approach. We have several equations and we just eliminate variables one by one until the only variable left is t, and that's the parameter that we need in our equation of the line. Another way to do this is using a little bit more vector notation. And vector operations. So for the vector equation of a line, we're going to need a point and a direction vector. So to find the vector, the line of intersection is in both planes. Well, if it's in both planes, if it's in the plane, it's perpendicular to the normal vector. So if it's in both planes, it's perpendicular to both normal vectors. So one vector that's perpendicular to two other vectors means it's just the cross product, or at least in the same direction as the cross product. Okay. And then to find a point, you need any point. So the easiest way to do that is just set one variable equal to 0 and then solve out and get another point. So we already know what the normal vectors for each one are. So to find the direction vector of the line, you just take the cross product. So you do that cross calculation, and you get 8, negative 2, 26. So notice how quickly we got the direction vector. Quickly, given that you have to do a cross product. And then to find a point, you still have to do a little bit of algebra. I lost some of my ink here. Okay. So here we just need a point, so we just say let x equal 0. That'll simplify things. And if x equals 0, then your two plane equations just become two equations in two variables, and you just solve for y, solve for z, and that gives you the coordinates of a point in the plane. And then once you have, a point on the line of intersection, which is in both planes on the line. Okay. So then I like to write the equation in vector form. So notice that you can answer this question either way. Either using algebra operations or using vector operations, taking the cross to get the direction vector. And let's just take a moment to show that these solutions are actually equivalent. So notice that the point that you get is the same point in both cases. It didn't have to be, that was just a coincidence. But now take a look at the direction vector. Are the direction vectors identical? Well, they're not identical, but they're the same direction. If you look at the first vector, just multiply it by 8. Multiply it by 8, and you get the second, and you get the vector the direction vector from the vector operations. So they're different magnitudes, but they're in the same direction, which is all we need. We need a direction vector. So long story short, you can do this either with the algebra or vector operations. Okay. So next, we talk about the distance between a point and a plane. So the key idea to developing the formula is to understand that if you have this point, the way you find distance is by drawing a perpendicular line. That's always true of distance between two objects. But a perpendicular line in terms of a plane is the normal vector. So what we want is we're going to say, well, let's just say there's some point in the plane. What we want is not the distance between these 2 points, but rather the perpendicular component of that distance. So perpendicular component means we want to take the projection onto the normal vector. And the way you do that is with the dot product. So what we want is not the distance between random point and our point in space, but rather the projection, which means multiply that vector, the length of that vector times cosine theta. But we know what that means is that we take it with the we take the dot product and then divide by the magnitude. Okay. So it winds up. So the formula works out like this. So that vector is p1 minus p0. And then I'm going to split that up. So p1 minus p0 dot n, you split that up into 2 parts. It's just p1 dot n minus p0 dot n. And now we break it down into the components. So p1 is our point x1, y1, z1. And then p0 is some point in the plane x0, y0, z0, dotted with the normal vector, which we've called abc. So you get these expressions. And we're going to divide by the magnitude of the normal vector. Normal vector was abc, so it's just the square root of a squared plus b squared plus c squared. Okay. Now the last step is to realize that this actually just comes from the equation of the plane. And since p0 was a point in the plane, we know what ax plus by plus zz will be. It's going to be negative d. So minus negative d just becomes d. So put it all together, and it gives you this formula. So where the point in space is x1, y1, z1, the distance between your point and your plane is going to be ax1 plus by1 plus cz1 plus d, absolute value. Or in other words, just plug it into the equation of the plane, divided by the magnitude of the normal vector, square root of a squared plus b squared plus c squared. So let's see how that works in a problem. So find the distance between this point and this plane. So what do? On the top, you simply plug in that point to the equation of the plane. So 3 times the x value, let me see, minus the y value plus 2z. Oh, and then what do we do here?
Move the 6.
We have to move the 6 over. So we have to realize this is 3x minus y plus 2z minus 6 equals 0. So minus 6. And we want the absolute value of that because we want a distance, divided by the magnitude of our normal vector. So over 3 squared plus 1 squared plus 2 squared. And so that works out to be 15 minus 4 is 11, plus 2 is 13, minus 6 is 7. So 7 over the square root of 14. And that's the answer. So the derivation is geometrically interesting, but it gives you a simple formula that's very easy to use.
1.87.
And that's about 1.87. Okay. So that's the distance between a point and a plane. The last one is the distance between a point and a line. So geometrically, what does this look like? Well, once again, here's the point and here's the line, and we're going to think of it in the same way. There's some point P in space that we want the distance to, so we're going to imagine that we have some point on the line, any point, and those 2 points form a vector, but what we want is the distance, which comes from drawing a perpendicular line. So we're going to take so we want that component. So how do we get that component? Well, notice that in this case, in the equation of a line, we don't have a perpendicular vector, we have a parallel vector. So this component, instead of it being a result of cosine theta, our angle is over here, so it's going to be sine theta. And we know that sine theta comes from the formula for the cross product. So that's what we're going to use. Sorry? Okay. So, right, so there you go. So we're going to take our made up our vector between our known point and some point on the line and cross it with the direction vector and then divide by the magnitude of the direction vector. And that'll give us what we need. Oh, why is it doing that? Okay. So find the distance between this point and this line. So how does that work? Well, first we need to form our vector. So our vector goes between our point in space and a point on the line. Well, what's a point on the line? Hey, it's right there. Right, and we know from the form of the equation that's a point on the line. So now we need to make that into a vector. So the vector QP, if you like, equals 8, 2, negative 5 minus 6, 2, 1. And that's just 2, 0, negative 6. Okay? We already have our direction vector. That's also written right into the equation. That's 3, negative 3, 4. So now we're going to take QP cross V, and that's 2, 0, 6 cross 3, negative 3, 4. And to get that, you get 0 times 4, that's just 0 minus negative 18. So 18, and then 6 times 3 minus 4 times 2. 18 minus 8 is 10. And then negative 6 minus 0, so you just get negative 6. Okay. So there's the cross product. So the distance is going to be the norm of that divided by the norm of our direction vector. And our direction vector was 3, -3, 4.
When you say norm, you mean the magnitude, right?
And by norm, I mean magnitude, yes. Okay. Right. And so now it's calculator time.
That's supposed to be 20 minus 6.
I wouldn't change anything.
Right, so let me fix that.
It wouldn't change anything because the distance is square root.
Changes it. Okay, so let me make those corrections. So after some fixing, here are the correct calculations. So it winds up being the square root of 1036 over the square root of 34. With the, first of all, with the cross product corrected to -18, -26, -6. And then you wind up with that square root of 1036 over the square root of 34, and that's approximately 5.52. So that is the distance between the point and the line. So to help you remember the formulas, one for the distance between a point and a line and one for the distance between a point and a plane, it may be helpful to remember this. When you're finding the distance from a point, when the other object is a line, the vector that you're using is parallel to the line. So finding the component requires sine theta, and that involves the cross product. That's the problem we just worked on. In contrast, if their object is a plane, the vector using your calculation is actually perpendicular to the plane. So when you try to find the component, you're using cosine theta, and that involves the dot product, as in this situation right here.